Hello everyone and welcome to this series of videos on fracture mechanics. So in this series of videos I'm going to approach fracture mechanics from another point of view by getting into the detail of some of the solutions which actually were quite useful in the evolution of the fracture mechanics. And to do so I use elasticity and continuum mechanics along with Maple, which is a code device for symbolic operations. You can use any similar kind of code like Mathematica, MATLAB, or SymPy in Python. So let's get it started by Kirsch Solution to an infinite plate with a circular hole. So basically, if you have a domain without any irregularity or any kind of hole here, let's say, you know that the stress is uniformly distributed through the domain. So if it is under uniaxial loading, you will have this uniaxial tension all over the domain. By the introduction of this irregularity, or specifically here for this case, a circular hole, you will see that there's this disturbance in the stress field around this hole. So we're going to see how the stress field actually is disturbed around the circular hole. We have this infinite terminology here, and let me just clarify before getting into the solution. So by using infinite, I mean that the geometrical dimension of this hole is way too smaller than the boundary. So the tractions on the outer boundary, on the external boundary, will not affect this circular hole. So let's get it started by getting into this solution strategy here first off. So as I said, I'm going to use the elasticity approach to solve this problem. And here the I'm going to use the two-dimensional solution, which is mostly used in elasticity problems using the concept of area stress function and the biharmonic equation. So using this strategy, we have an area stress function, which is a kind of potential function. We assume it and we basically plug it into the biharmonic equation, which is this equation here, del 4 phi equal to 0. This del operator is this is the del operator or nabla here, and we actually try to solve this. And since we assume this potential function, we need to find some of the constants here using the biharmonic equation here. So because we are going to fulfill this, and also the the boundary conditions here. So we use the boundary conditions to find these constants here, and using this, just going and back, we actually go and back between these two states here to find the proper phi. And after we found it, we solve for the constants, as I mentioned, and finally we get our phi here. So the final phi should actually satisfy the biharmonic equation first off, and also should satisfy all the boundary conditions. If that is the case, we continue to the next stage. Otherwise, we need to get back and revise our area stress function. Uh, unless we go and calculate the stress components from the area stress function, and then we find the stress from stress strain relation, whether it is a plane stress or plane strain situation, and then we solve for displacement from the displacement strain relation. So this is the overall solution strategy. You can find it in any kind of elasticity book. So to find it, or in order to select the proper term from the solution of the area stress function, we need to start by writing our boundary conditions. So if we write the boundary conditions here at infinity or on the external boundary, we see that in the Cartesian coordinate system, we have sigma x equal to t, which is the uniaxial tension here, and we have sigma y and tau xy equal to 0. So if we convert this, if we map this or transfer this to the polar coordinate system using these equations here, where you can find in any kind of elasticity book, or even you can prove them using the Mohr circle, you can find this kind of stress field on the external boundary. And as you see here, you have cosine 2 theta terms for sigma r, which is the radial stress. We have the sigma theta, we call it here hoop stress, and shear stress actually contains sine 2 theta term. So by knowing this actually stress field at infinity, and also by knowing the boundary condition on the whole, we will be able to select the proper terms from the area stress function solution. So here on the boundary conditions, we have this element of a stress here. We have the radial stress, the hoop stress, and the shear stress. So I just simply assume that the radius actually increases in this direction. So we have sigma r increasing in this direction, theta increases in this direction, so sigma theta increases in this direction. And the opposite actually gives you the direction on the opposite side of the element for sigma r and sigma theta. For tau r theta, we actually you know that theta increases in this direction, so we just put this here, this arrow, we put it in the positive direction, in the, let's say, in the increasing direction of theta. And here we have this, let's say, arrow in this direction, which is the direction of increasing r. And we have the opposite direction on this other side of the element. So if we move this element and put it here on the boundary of the hole, we see where the material is present, of course, because here the material is absent. This is a hole. So we see that we only have sigma r in the opposite direction, and we have this tau r theta here downward. But here, since there's no stress, we see that these two stress components are 0. Next, we have the Michel solution to the biharmonic equation in polar coordinate, which is because we're going to solve this biharmonic equation, and we also need that our selected phi or area stress function actually satisfies this biharmonic equation, as well as our boundary conditions, of course. So we have this solution, we have this equation, and this solution is actually the solution to this biharmonic equation was first given by Michel and actually evolved through years in this form. And I got this from Sad Elasticity book, but you can find it in any other elasticity book. So if you have this phi, this potential function, and if you plug it into this biharmonic equation, it will satisfy this equation and it becomes 0. But we cannot select all of this term because some of them are redundant and we need to get rid of them. So we're going to select the proper term. But which term to select? So a methodology was actually used by Dunder and later by Barber, and I also inspired by this this table here, that for each and only term, you can actually find sigma r, sigma theta, and tau r theta for each term in phi solution. And then you can actually from here find the proper term you need to select for the area stress function. So for example, these are all the terms in the area stress solution, and here are the corresponding sigma, the radial stress, hoop stress, and shear stress, where actually they have been extracted from these kind of, equations, this set of equations here. So since I'm going to find for the stress components here at infinity, where they can yield actually cosine 2 theta for sigma r and sigma theta, and sine 2 theta for tau r theta for the shear stress, I'm going to select the terms that contain actually cosine 2 theta here for sigma r here, and sigma theta, and sine 2 theta for tau r theta. So all these terms does not yield what I want, but when it comes here, I have cosine n theta. So if I put n equal to 2, I will be able to see that actually cosine 2 theta appears here as well as here, and for tau r theta, sine 2 theta actually appears here. So I'm going to select those kind of term which yields what I want at infinity. So these are not the terms which are suitable. So the only suitable terms are these 4 rows here. So here, 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 and here, which are suitable for my area stress function. So I'm gonna plug them into this phi, and then I'm going to find the constants here by using these boundaries, these boundary conditions here at infinity, as well as these boundary conditions here at this threshold. So I will be able to find these constants. For example, I have this a n1, n2, n3, and n4 here. So I will be able to find these constants. So let's switch to Maple to find them. So I restart everything and I load some of the packages which I need for the plot. So next I have my area stress function, which is essentially this kind of terms that I selected from here. So if I go here, you see that I selected these kind of terms along with some of the terms here, some of these primary terms here, these 1, 2, 3, and 4 terms, along with this row of terms in phi to solve the problem. So I have my phi as this. And actually I removed, let's say, this A0 because this does not affect our solution, as we're going to actually differentiate with respect to R, and in some of the cases we're going to differentiate differentiate with respect to R or theta, so this will actually remove and it does not affect our phi solution. So as I said, we need to first of all, we need to satisfy the biharmonic equation, but we know that actually Michel solved the biharmonic equation. So this one is this stage where this kind of solution is completely redundant. But if you use it, for example, in Cartesian coordinate system, we have to also make sure that this will your selected phi actually will satisfy the biharmonic equation. And here I have sigma r equal to this sigma r, sigma theta, and tau r theta, which I actually just put here in Maple. So you have your sigma r equal to this expression, sigma theta and tau r theta. And in the second line, basically, I said that these are functions of sigma of r and theta. So sigma r is a function of r and theta. So as you see here, at infinity, my stresses are bounded. I have only this t, or let's say these kind of terms here, so there's no sign of any infinite or unbounded term. So I need to remove those kind of terms which actually create an unbounded solution, uh, an unbounded stress in my solution. So as you see here, in sigma r, if you look at, so as r goes to infinity, this term will go to 0. We don't have r here. So ln r here, this term actually yields unbounded stress field at infinity. So we have to get rid of it. And we also have cosine 2 theta, nothing here, R4, and everything is fine here for sigma R. So again, here we have A through E. And when it comes to here A22, we also have this R squared term here, which also yields unbounded stress field at infinity. We need to get rid of it. Also, it is here A22. We need to get rid of it. Nothing here. Tau r theta, which I just use t instead of theta here. So this again A22 creates an unbounded version of stress. So we need to get rid of these two coefficients so we actually put them equal to 0. So if we just execute these lines, you see that these A3 and A2 actually are removed. And if I just execute this phi again, you will see that these are also removed from this here. So they are redundant terms. We don't need them. So we have stresses at infinity, but let's say in Cartesian coordinate system. Let's add this. And if we look at, so I have these terms here, and so I have sigma x, sigma y, and tau xy. Then I'm going to transfer them to the polar coordinate system using these kind of equations that I wrote here. So I'm going to transfer them to the Cartesian coordinate system. So I have these coordinate systems here. I have these transferred stresses here, and and I also did another kind of operation because in some of the points here, Maple actually, since I actually used the infinity instead of r, because I want to say that at infinity, at the radius of infinity, at infinite distance of in the domain, at the infinite distance in the domain, actually, I'm going to say that these terms actually tend to 0. But Maple does not understand this, and I substitute this undefined here with, let's say, 0, because we know that if r goes to infinity, this whole term goes to 0. So for the sake of, illustration, I'm going to show you this. So let me just remove this BC here. So if I unsign it here, so this does not show it. Let me just clear everything and remove this term here. So if I execute everything, so you will see that this term, actually the first term in sigma r, actually becomes tends to 0. So we have a series of undefined terms here, 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 and there. So I'm going to just replace this with 0 because we know that this is mathematically 0, but Maple does not handle it. Okay, and we also substitute it with colon here. So for the tractions on the edge hole are equal to A, as I said, we have sigma r and sigma and tau r theta equal to 0. So we also have this equal to 0. So now we have 1, 2, 3, 4, and 5, let's say boundary condition here on the infinity and on the edge hole, on the whole edge, sorry. And then we have, and if we look at this boundary condition here for sigma r on the whole edge, you'll see that we have a series of terms where the coefficient is cosine to theta. However, the rest of the terms, they don't have any coefficient. So we can just break this into two separate equations here. So this actually equal to 0, and the rest should be equal to 0. So if I just rewrite them as BC41 and 42, here I also said that we break this into two equations. So I will have the boundary conditions, the new version actually is 4.1 and 4.2. And now I have my BC1, BC2. I don't get anything. Maybe I also get a 2.1 from here because this is equal to 2a21 sine 2 theta equal to minus t divided by 2 sine 2 theta. So I can get rid of this sine 2 theta. So I can find a 2.1 here. So I have BC1, BC2. I actually use BC5, BC41, BC42, and I solve for these kind of, for the rest of, the unknown coefficients in the area stress function, and I also assign them. So I will have these equations here, these kind of constants here. So since I assigned them, so I can rebuild my phi here. So this is the phi that is the solution to the biharmonic equation, and also this is supposed actually, so we have to just check it out. So we know that it is fine because already Michel solved the biharmonic equation, so we don't need to recheck this. But let's check all the boundary conditions here one by one here in this loop. So for boundary 4 and 5, this is 0 equal to 0, what we expected, and this is half cosine 2 theta plus 1, half cosine 2 theta plus 1 t, this is fine, minus half cosine 2 theta minus 1 t, and this is also the same. And we have here minus t sine theta cosine theta, which is equal to minus half of t. This is sine 2 theta, so this becomes 2 sine theta cosine theta. Actually, these two cancels out each other, so this is also equal to this. So we can say that, okay, the biharmonic equation is satisfied, and also our boundary conditions are satisfied. So we are at this stage where we checked also the biharmonic equation satisfies, and we checked all the boundary conditions. These are all satisfied, so this is true. So we go and calculate the stress components next. So since we assigned everything, we just need to press this sigma r, and sigma theta, tau r theta lines, and then execute each and every. So if you want to get the stress strain, here I solved it for the plane strain case here. So you can use these equations here for the plane strain case actually. And you have these kind of coefficients here, lambda and mu, which are the Lamas constants here. And we have E as the Young's modulus, nu is the Poisson's ratio, and mu is the shear modulus here. Next, we have the displacements. So if you have the in polar coordinate or cylindrical coordinate, you can correlate the displacement with the strains using these equations here. So if I call this S as a strain, the first equation, the second equation, and the third equation, and if I solve them simultaneously, so I will be able to get ER, E theta, and ER theta here. So next, I'm going to solve for the displacement. So I have the strain displacement, the first equation is this, the second equation, and the third equation, which are essentially these equations here. So I desolve because this is a differential equation. So I use the desolve command here in Maple, and I solve for UR theta from the first one, and the third one actually gives me the U theta. And these constant terms F1 and F2 theta actually are those related to the rigid body motion, or you can actually find them using your initial condition for the displacement. You may say that, okay, so at for example, this point of the problem actually you may say, since this is actually under tension, so you may say that, okay, so the y for this point, the y coordinate actually does not move, but you know that x actually does move. So you may say that since this is under uniaxial tension, so this may become like this, like an oval shape, a horizontal kind of oval. And here you may say that, okay, so y may move down from this point, but x is actually, x does not change. So you may use this point and this point for y being constant and y being constant, and here for x being constant, and using this initial condition to solve for the displacement for this kind of problem. So it depends on what kind of problem you assume to solve. And here we're going to polar plot the stress components here. But here we know that if you plot various kind of stress components, you will see that sigma r has the highest value here. So this can also be as it can also be left as an exercise to you to plot all the stress components, and you see that sigma theta is actually has the highest value in the vicinity of the hole. So if I use the polar plot, you will see that and I normalize it with T with the far field stress, you will see that here on the half pi and 3 half pi, you will see that stress is the highest hoop stress has the highest value, which is almost 3 here, but we will find the exact value later. So this is almost 3. So this becomes actually quite critical in let's say here and here. We have high stress concentration or high amount of distortion here and here. And if we plot this along the, let's say, x-axis, so if we plot sigma theta along the x-axis to see how it varies, we get a singular kind of, solution. Here we have like r divided by a, So we normalize it, and we have the hoop stress at half pi and also normalized by R over A, and the whole is normalized by far field stress. You will see that it goes to 3. So, and it goes to infinity in fact, but here it goes to 3 here. So we have a singular kind of solution, a singular kind of behavior, not solution, because this is not singular, but this is like a singular kind of behavior here. So if we want to calculate the stress concentration factor here at, let's say, half pi and 3 half pi here and here, so I evaluate sigma theta at on the whole on the whole edge and half pi, and normalize it by the the stress field at infinity, or let's say a plate or a domain without any irregularity. You will see that this becomes 3. So this is what we get here, and also Kirsch got a 3 as the stress concentration factor. So this actually uh, summarizes the solution to the Kirsch problem for an infinite plate with a circular hole.